All right, time to start learning about statically determinate trusses. That means we can use equilibrium to solve them. Um, and their trusses. By the end of this lecture, you should be able to determine if a coplanar truss, so a 2D truss, is statically determinate or indeterminate, and if it's stable or unstable. Then you can also analyze that statically determinate truss using either the method of joints or the method of sections to determine the support reactions and the member forces. And then we should also be able to identify zero force members in the coplanar truss. Now, again, we're talking about coplanar trusses, which means we're talking about 2D trusses. Every member is in the same plane. There are 3D trusses called space trusses. We're not going to be getting into those in this course. So, yay, trusses! Here are some examples of different types of trusses that have been developed over the years and are used. We often see them in roofs, supporting roofs, on bridges, supporting bridge decks, either above or below. And those are just the various ones that you will see out there. Get a little bit of truss terminology here. I know, I always like knowing vocab words, right? First we have the top and the bottom, right? The top horizontal member is called the upper chord. The bottom is called the lower chord, right? Makes sense. Then we have these diagonal members called diagonals. Very original. And then if we're talking about the overall structure, we have the span of the truss, which is the length, and the rise, which is the height. Generally, you think of trusses as longer than they are tall. Doesn't have to always be the case, but So those are the different types of words you might hear when someone is talking about a truss. Some assumptions for my analysis of statically determinate trusses. One, we assume that each connection is a pinned connection. If you remember, pinned connections can only transfer force. They can't transfer moment. And since we're talking about a 2D coplanar truss, that means we have Fx and Fy being transferred only at each joint. The joint can only transfer horizontal and vertical force. Well, it can only transfer force, and those components can be broken up into the X and Y components. Two, I'm only going to apply loads at the joint. Right, if I look down at this truss right here, I'm only applying loads at the joints. if I were to apply a load between joints, that would cause bending in my member, so I don't want to do that. So I'm only gonna have loading applied at the joints. And finally, I'm going to ignore my self-weight. Compared to the loads that I'm going to be applying, the self-weight is negligible. Now I mentioned I don't want to apply any loads on the members, not at the joints, and that's because I want my members within the truss to remain axially loaded only. They're not going to have moment, they're not going to have shear, they're only going to have axial load. And that means I will either have tension, right? Tension on my members, if this is a member, which I'm going to assume tension is positive, and I often denote tension with a T, or the other way, compression. Denoted with a C, and compression is negative. Okay? Only axial force, tension or compression along the length of the member. No bending, no shear, no moment. So how do I determine if I have a statically determinate or indeterminate beam? Truss? Well, as we talked about earlier, I need to see how I can relate my number of unknowns to my number of equations. How do those relate? That'll determine if I'm statically determinate or indeterminate. My unknowns are my reactions at the supports, R, and the forces in the bars. Forces in the bars are the members, right? Forces. I'm trying to write farces. Forces in bars, members, B. I don't know my support reactions, and I don't know the forces that are in each individual member. I do know that I can use equilibrium. I can solve for the sum of the forces in the x direction and the sum of the forces in the y direction. There are two equations of equilibrium at each joint. At each pinned joint, I can only, at each pinned joint, it's a pin, right? So I can only have moments, or I can only have forces, I can't have moments. If I take the sum of the moments about that joint, it better be equal to 0. So I can only have the sum of the forces be 0, and the sum of the forces in the x direction be 0, and the sum of the forces in the y direction be 0. So, and each joint that I can use J for my number of joints. So my number of unknowns is R plus B, my reactions plus my forces in the bar. My number of equations is 2 times the number of joints, because I can solve for the forces in the x and the force in the y at each joint. And if those are equal, then I have a statically determinate beam. Truss. I keep saying beam. Sorry. If I have too many unknowns, then I am statically indeterminate. Right? I have too many unknowns and I don't have enough equations to do it, right? How do my unknowns compare to my number of equations? Hopefully you've been doing stuff like this since algebra, right? So that's how I determine if I have a statically indeterminate or a statically determinate truss. Add up my reactions, my forces in the bars, and compare it to how many equations of equilibrium I can use based off of the number of joints, J. Now, if we're talking about stability, I'm going to compare my number of reactions and forces in the bar to the number of joints, equations associated with the joints. If I have not enough reactions and force members, I'm unstable because I'm partially unconstrained. I'm partially constrained. All right, that was similar to when we talked about just over stability as a general concept. If I have not enough reactions compared to the number of joints, the number of equations, then I'm unstable. Meanwhile, I could also be unstable if my number of reactions and my member forces is greater than or equal to 2 times the number of joints. That would be if I have reactions that are concurrent or parallel, or if there's a collapse mechanism in it. A collapse mechanism within the structure. So if my truss support reactions are concurrent or parallel, or if there's a collapse mechanism. within the structure. I'm going to give some examples of what those mean. So, having your support reactions concurrent or parallel means that you have an external instability. That means it affects the entire structure as a whole. If you have a collapse mechanism within the truss, that is internal stability or instability. That means internally there is something wrong that your structure will collapse because it's unstable. So we have two different types of stability, external and internal. External refers to the thing as a whole. Internal refers to something within the structure. So I'm going to take a look at external stability first. That means that the entire truss itself is unstable. For example, if I look at the bottom left, right? If I look at concurrent reactions, let's see, I have a reaction. If this is A and this is B, I have a reaction at A in the X direction, reaction at A in the Y direction, and a reaction at B in the X direction. If I apply a horizontal load up here and I take the moments about A, well, you notice RAX, RAY, and RBX, the line of action, all converge at A. So I would have to do RA X times 0 plus RAY times 0 plus RBX times 0 minus P times whatever this distance is. D. Well, let's see. That's 0. That's 0. That's 0. So the only way this is valid is if PD is equal to 0. So I either have no force or the moment arm is 0. And then you just get 0 equals 0. Right? So that's the fact that all of these reactions have a line of action that converge at the same spot. Now, if we have parallel reactions, again, let's say I apply a load in this direction. Well, you can see these are all rollers and they only act in the Y direction, right? So if I sum the forces in the X direction, I sum the forces in the x direction, the only force acting in the x direction is my applied load P. So the only way this doesn't move to the right is if I don't apply that load, right? It's just, you pull on that and it's just going to go along for the ride to the right because all I have is rollers. I have nothing holding back my truss. So this is talking about the entire structure working as a rigid body. The entire structure is stable, unstable. If I have concurrent reactions or if I have parallel reactions, right? Rigid body means the entire thing moves. The entire thing either rotates or the entire thing shifts to the right or shifts to the, up, down. But the entire thing moves, which is why it's called external stability. The next thing to talk about is internal stability, which means there is some sort of collapse. So here I have this truss, and I'm going to try my darndest to draw a picture. Let's say I apply a load right here at B. Well, what would that look like? Okay, this member starts displacing. Let's make that a little bit thicker. This member starts displacing. This guy comes, oh, but he's still attached there. This one will probably come like that. Right? And then this, well, you see there's a roller over here, right? So this whole thing could just basically come along for the ride. There's nothing holding this thing down. So that means the more I pull, the more I apply this load, I'm just going to eventually collapse the entire structure. This would be a great time to pull out some Tinker toys or something, Connects, I don't know, to play with, talk about instability. But there you go. External means the entire thing moves as a rigid body. Internal means the truss collapses on itself. And I'm going to pause right here and pick up in a minute.